Hi, everyone. I'm Gijs de Boer. I'm currently the chair of the Environmental Science and Technologies Department at Brookhaven National Laboratory and was previously a senior research scientist at the University of Colorado. My research involves looking at the physics and chemistry of the lower atmosphere and understanding how parts of the atmosphere contribute to our daily lives. That bridges everything from formation of clouds and rain and sources of energy to the weather that we experience on a daily basis. Weather impacts our lives in many different ways, some ways that we know and understand, and other ways we don't. Clearly, if you have a sporting event that you're going to and it's going to snow like crazy or rain like crazy, it may be a less enjoyable experience, or maybe your flight gets delayed because of bad weather, or maybe there's a lot of traffic because there's some flooding on the road or something like that. Those are all the things we experience in our daily lives. At the same time, there are a lot of other elements of our daily lives that are impacted by weather in ways which we don't necessarily see. And so when we think about the energy we use, for example, um, that energy at some point had an environmental connection. And some of those are very direct when we think about renewables and solar power and wind energy and things like this. Some of them are far less direct when we think about things like heat waves or cold snaps where people crank up their AC or maybe crank up their heat. That really drives big energy spikes and dictates how much energy is available for society. I really appreciate how relevant the research is in terms of many of the aspects that I just introduced, on how weather impacts our daily lives. I also appreciate working with people who are excited and motivated and enthusiastic about the science that they conduct. And that is everybody from, high school to undergraduate students who are just learning about a certain field to people who have been working in environmental science for 30, 40, 50 years. Everybody has a good passion for what they do in this field. And it's really invigorating, I would say. I got into environmental science and atmospheric science um, at a fairly young age, I would say. So, a little bit of history from my side. My father was a merchant marine captain and sailed all over the world in big cargo ships. And of course, he was very keenly interested in weather. When he stopped sailing and took a desk job, a lot of that interest in weather kind of perpetuated because his desk job required that he was aware of weather conditions at certain ports where his ships would be coming in and he would be dealing with port operations. And so, from as long as I can remember, I've been exposed to some kind of weather forecasting and weather monitoring. And so I think when I was starting to look for opportunities for school and areas of study that I might be interested in, meteorology became high on the list very early on. And so I majored in atmospheric sciences as an undergraduate and then went on to graduate school to do more of that. Ended up going down the path of being a research scientist and pursuing knowledge in the environmental sciences. As a graduate student, I became very tied to the Arctic, and all of the work that I did on my dissertation was focused on clouds in the Arctic environment. And so that was kind of an initial push towards northern high latitudes. And that stuck with me as a postdoc and early into my career at the University of Colorado. And it was right about that transition in 2011 or 2012 or so, where a group at the University of Colorado was starting to discuss this idea of a very large expedition to the Arctic. And I was lucky enough to be in the right place at that point. I mean, this was not my brainchild, but there were certainly a lot of interesting and exciting elements to that. And we felt like we had some things that we could contribute to the broader project with our drones that we were working to develop at that time. So that's how I became engaged with MOSAiC, and it was a ride. It was certainly, 10 years or so of planning and a lot of meetings, a lot of preparation, and it was amazing to see it all work out. MOSAiC is the multidisciplinary drifting observatory for the study of Arctic climate. So the broader MOSAiC project was a 1-year expedition to the Central Arctic Ocean, and it was based on a German icebreaker, which was frozen into sea ice in the Arctic and then allowed to drift with the sea ice as it moves. So sea ice is not a stationary entity. It's kind of like water. It moves with the water. And so when the ship was frozen in one part of the Arctic, the expectation was, based on historical drift patterns, that it would come out in a very different part of the Arctic. And so that plan was in place so that we can track over the course of a year the fate of sea ice from being frozen in the fall to melting in the spring or summertime. It's important to distinguish between all of MOSAiC and the small part that we conducted with the drones. For the all of MOSAiC question, this is a huge, huge undertaking, right? You're talking about setting an icebreaker into the Arctic ice and letting it drift for a year. You're talking about trying to keep people fed and safe. And in terms of our project, there was also a lot of planning that went on. Clearly, being in the middle of the Arctic Ocean makes it very challenging to make some, easy changes to the equipment that you have, or even to transfer files back and forth so that you can see whether the data quality is good. And so we spent the better part of 2.5 years training our teams, talking through contingencies, understanding how our equipment worked in the Central Arctic Ocean. We actually did a pre-trip to Svalbard in Norway, so that we can go fly at very high latitudes in a challenging environment. And there are all kinds of reasons why the equipment may not work as well at northern high latitudes or any high latitudes as it does when we're at home in Colorado or out here in New York. But there were actually a lot of different unique opportunities for atmospheric science. There are very, very few measurements in the Arctic generally, and most of those measurements have come from land-based observatories, and those are distributed around the Arctic. For example, we have some very nice facilities in northern Alaska that have been collecting data there for almost 30 years, or actually maybe pushing 30 years right now. In terms of atmospheric measurements near the surface in the Central Arctic Ocean, over winter in particular, the number of data sets we have is very small. There's some very specific phenomena of interest there. Of course, there is the broader atmospheric chemistry, the dynamics of the lower atmosphere and over the sea ice, and the formation of clouds. Those are all interesting to us. But particularly with a changing ice environment, which has seen over the last decade or two a thinning of the sea ice and a much more mobile sea ice pack, there are a lot of questions about how the surface and the atmosphere interact with one another, how different energy or other things are kind of, I don't know, cycled between the atmosphere and the underlying ice and ocean, and also how differences in the ice properties impact what's happening in the atmosphere. So one of the things that we were specifically targeting while out there was what's happening when the ice breaks apart. And the ice is really dynamic. You have it constantly kind of moving and shifting, and that forces these kind of cracks to form in the ice that can open up and expose the atmosphere to the water beneath it. And in that environment, you have a lot of transport of heat from the ocean surface, which is near freezing, to a much colder atmosphere over the top of it, as well as moisture that is then coming off of the open water into the atmosphere. Oftentimes you see clouds forming in these environments. You also have the transfer of little atmospheric particles, whether those are biological in nature or otherwise. You have these aerosol particles forming over the ice, and those are really important because when you think about clouds specifically, every cloud droplet forms on a particle in the atmosphere. And so when we think about clouds in the Arctic, which drive a lot of climate-related questions about energy from the sun coming to the surface, or some of the heat energy from the Earth going back to space, all of those cloud droplets are forming on these little atmospheric particles. And so when you open a whole new source of particles to the atmosphere, it's a very important part of the overall budget for the Arctic. Drones fill a very unique gap. And often when we have these types of observing activities, we have surface-based sensors that do a really good job of collecting very fine detail on what's happening right at the surface or close to the surface if you have a tower. We launch weather balloons every so many hours for MOSAiC. Those balloons provide one quick profile through the atmosphere, and then they keep going. And on top of that, we also had helicopters for MOSAiC. The helicopters were not really equipped to make very many atmospheric measurements, only at very select times. And tethered balloons, which are also doing kind of the same thing, except they're on a tether, so you can control the altitude a little bit better. Those tethered balloons offer some unique perspectives at one point in the atmosphere, depending on which way the wind is blowing. What the drones allow us to do is they allow us to very quickly profile, so we can collect really high resolution data on how the atmosphere is evolving over time over a certain layer. They allow us to sample in clouds or around clouds specifically, and they allow us to look at spatial gradients. So thinking about how properties are changing over some distance. And this again becomes really important when we think about things like cracks in the ice, where you have a clear input into the system that might be a half mile up the ice a little bit. And so you can take the drone and fly across that event and look at how the atmosphere is changing on one side versus the other. That's really difficult to do with surface-based sensors or balloons or other things like this. The other thing that the drone allowed us to do was map the sea ice in high resolution. We get information on the ice from satellite-based imagery. The satellite-based imagery is very useful in that it covers a very large area, but it's often impacted by cloud cover, which then blocks the sensor from the surface, leaving holes in the data. And ultimately, the resolution is maybe not what we need it to be at times, just because the sensor is way up in space and you can only get so much resolution out of the instruments that are flying. So with the drones, we can do very careful mapping of the ice surface and get high resolution measurements of things like the fraction of melt ponds in the ice in the springtime. As the ice is starting to melt, you start to build up water on the ice surface, which changes how much heat is absorbed by the ice, as well as the broader reflectivity of the ice over some area around the ship. We brought 3 different aircraft types with us. We brought in total about 25 aircraft. The 3 types that we brought, they were all small UAS, as we call them. These are aircraft that are under 55 pounds when they fly. The largest of our aircraft had about a 2-meter wingspan from one wingtip to the other and weighed about 20 pounds. That's a fixed wing plane, meaning that it's like a normal airplane that we think about with a propeller and 2 wings and flies mostly horizontally. We had another fixed wing aircraft called the Data Hawk. This is a smaller aircraft, about 1 meter across. And then we had a multi-copter system. So this is maybe more like the drone that people think about, where it has six propellers and flies more like a helicopter. What the multi-copter did for us is it provided a stable platform for making measurements of the ice surface. I mentioned earlier mapping the ice surface. What we did on the multi-copter is we put 2 different gimbal systems on it, one for the bottom, one for the top. And each of those gimbals held a sensor to measure the amount of solar energy impacting the sensor. And so the upward-looking one was literally looking at the sun, whether it was cloud-covered or not. It was collecting information on how much energy from the sun was reaching the drone. The downward-looking one is looking at the surface to look at how much of that energy is being reflected off of the surface. And this comes back to understanding the energy budget of the environment and how much energy is going into the surface and heating the surface versus how much of it is reflected and going back towards space. So that was that system. The other 2 systems were both equipped to make measurements of some basic but important atmospheric properties. This included temperature, humidity, pressure, wind speed and wind direction, and turbulence. And we wanted to measure all of those quantities, again, to map in very high resolution how the atmosphere changed in response to certain surface features or in response to events that were taking place. These aircraft usually flew from the surface to about 1 kilometer up into the atmosphere and just did very frequent profiling to map out the stability and the mixing happening over that layer. There were lots of challenges. This environment is probably the most difficult you can find in terms of flying drones. It was very nice to not have a bunch of infrastructure nearby. So there are far fewer concerns about flying into something or, causing challenges or problems that way. But at the same time, you have a lot of icing conditions, which aircraft are not good with ice. Once ice starts to accumulate on them, it changes how the mass is distributed on the plane. It could result in a loss of propulsion. There's all kinds of problems that come about as a result of ice forming on an airplane. Lots of icing, extreme cold, which is difficult on the operators who were outside flying the aircraft. Very low visibility at times where we had fog and other things that made it difficult to see the aircraft. And again, this balance between all of the different projects and activities that were going on. People had to coordinate and cooperate and leverage the resources collectively. And so that is critically important, but it does pose challenges in terms of collecting the exact data set you want. It may be that when the conditions are just right, it's not your turn to be out there flying, and instead there's a different group doing something else. One of the big challenges that dictated how many people could be on the ice at any given time is that there was always a threat of polar bears around. And so we had bear guards who were out there to make sure that people were safe and protected, and also to make sure that somebody was looking for the bears. As a scientist, it's really easy to just put your head down and start working on things and not really pay attention to your surroundings as much as you need to. And so that restriction or that limitation as to how many people could be out on the ice at once was certainly um, one of the things that limited what we could do from a flying perspective. To my knowledge, it's the first time that we've collected UAS drone data over the ice for any reasonable amount of time at the latitudes that we did. Other ship expeditions have had drones on board. They might have made a few flights and collected some data. Here we're talking about 6 months. We're talking about going up to a kilometer through clouds in a very difficult environment, and we're talking about doing that as high as 88 north. So we were very close to the North Pole with some of these flights. We were flying in minus 20 degrees. It was pushing the boundaries of many different levels, I would say. And so I think there is a lot of unique information in the data we collected. And I think we've already seen several publications come out that highlight some of those new insights that have been gained about specific environmental phenomena. Ultimately, given all of the challenges faced in this environment and the fact that it's a very difficult environment to operate in generally, I think we did a fantastic job, and we got a lot of good measurements from a couple different platforms spanning 6 months of time. So it's hard to argue with that, and we'd love to do it again sometime and take the knowledge that we gained from this iteration and do it a little bit differently so that we're even happier the next time around. At that time, I was a research scientist within CERES, a Cooperative Institute for Research in Environmental Sciences at the University of Colorado, and I was an associate director for science within IRISS, which is the Integrated Remote and In Situ Sensing program there. The IRISS team is great. I think they have a lot of talent. They have a lot of skills, and they have a lot of experience. And I think the experience part is something that they bring to the table very uniquely. There are very few groups around the country who have been developing UAS specifically for environmental science topics for as long as they have. And what comes with that experience is not just an understanding of which aircraft do well and which aircraft don't, although that's a big part of it. You also have a lot of experience with the measurement systems, how to integrate them, the airspace regulations and requirements. You have lasting relationships with the FAA, which allow you to work with them to get flight permissions that may be more challenging for other groups to work towards. And you have an ability to continue to kind of push the envelope a little bit with regard to the technology because you're confident in what you have. I think the advice that I would give to scientists about using UAS in your research is that it takes some time. And I don't say that to scare people away from it, but the reality is that the experience that I just talked about with IRIS pays off big time when it comes to collecting not just measurements, but collecting accurate measurements and good measurements that can actually be used for science. And I've seen this many times with groups that are working to advance UAS technology for scientific purposes. I can't think of an example where it went right the first time. And, the plane flew or the drone flew and the measurement system often collects data. But when you really start to dissect it, you realize that the placement of that sensor isn't quite right. And therefore your data are biased in some way. Or, you didn't fly the pattern in an optimal way, and therefore you're missing part of the story. Or your permissions are limited to fly to only this high above the surface when what you really wanted to measure is double that height. Things like this, they just take time to understand and really implement. And that's not meant to scare people away. I hope people have the luxury of exploring all those things. But if you're just on the science side and you kind of get one shot at an experiment like MOSAiC, you want to make sure that your measurements are of high quality, and you don't want that one shot to be a proving ground for your equipment. Sometimes when I have a seminar, I'll open with the question of, have you ever dreamt that you can fly? I think we've all had some kind of dream of being able to fly, and I think the drones allow us to do that a little bit and collect unique measurements that help us to understand what's happening with our planet and help us to understand all kinds of factors impacting weather in our daily lives. So I guess that brings us full circle, and we're back to why I got into this in the first place. And I just really enjoy it. It's a lot of fun to have that opportunity to see things through a different lens.